Hello everyone, today we are going to talk about modular arithmetic. Modular arithmetic is a very cool concept that has many applications in group theory, especially in cryptography, which is in computer science. For our purposes today, we will only be given an introduction to modular arithmetic, and at least the amount needed to study group theory. So without any more further ado, let's begin. So, what is modular arithmetic? So consider the set of integers. Okay, so I have a set of integers z. Now I have a subset S, and the subset S contains the elements 0, 1, 2, 3, 4, and 5. Now, is S a group under addition? Now, let's recall what a group is. A group is just a set that's some binary operation that obeys these four properties over here. So it has to be closed under the operation, it has to be associative, there has to exist some identity elements, that's in G, such that A operated with E is A for all A's in G, and there has to exist some B, where B's in G, where B is the inverse of A. So let's check that. Okay. So first of all, is it closed under the operation? Meaning that if I add any of these elements, will I get another element that's also in S? Let's test it out. Say I add 2 by 3. 2 plus 3 equals 5. And 5 is in the set. What about 1 plus 1? 1 plus 1 is 2, which is also in the set. Well, what about 5 plus 1? 5 and 1 are in the set, so 5 plus 1 should also be in the set. But 5 plus 1 is 6, right? And 6 is not in the set. 6 is in the set of integers, but 6 is not in the set that we are considering S. This means that S is not a group. It's a set, of course. It's a collection of elements, but S is not a group since it isn't closed under addition. We could also check if it satisfies the other properties, but just knowing that 1 is invalidated, it means that S cannot be a group, unfortunately. So S is a subgroup of the integers, and the integers is a group under addition, but S is not a group. Now, there is a way to form subgroups of integers that are groups. Like with this example I've shown here, S is not a group. However, it is possible to kind of tweak math in a way to make subgroups of the set of integers that are actually groups. And that's where modular arithmetic comes in. So imagine if I take this set. So really here, what I'm saying here is that I have 0, 1, 2, 3, 4, and 5, right? Imagine if I take this line segment and kind of close it in on itself. Like take the ends here and close these ends in on themselves to form a circle. When we do that, we get this over here. So what I've done here is I've taken these endpoints, I've closed them together to get a circle. Now, let's call this circle, let me say, S prime. Now, is S prime a group under addition? Well, let's see. If I have 0 and I add 1 to 0, this corresponds to just going from 0 and going to 1, we get 1. That makes sense, right? So same with 1, if I have 1 plus 2, I have 3, which is also in the set. Same thing with here, 1 plus 2 was 3, and so on. However, what's 5 plus 1? Well, if we have 5 and we add 1, we actually get 0. This is really kind of weird in a way. How is 5 plus 1 0? Well, for the linear line, addition just meant going linearly forward. You go one step forward. But under this clock, addition is now rotating around the clock. So instead of like if you have 0 to go to 1, just go one step to the right. But here, instead we go one step clockwise. So in this way, 5 plus 1 is 0. For the line, 5 plus 1 is 6. Since the number line is now closed on itself, 5 plus 1 is 0, which is in the set. And you can probably see why we are doing this. Because no matter how much I add any number by, I will always get a member of the set. Since it's a clock, it's a circle, I can add 1 by a billion. Just go have a billion steps in a circle, and I'll always end up in this circle. However, for the line, if I add 0 by some number, I may get outside of my set that I'm considering. So this clock is actually called the integers z mod 6, I believe. Yeah, mod 6. It's called mod 6 because it has 6 elements. 1, 2, 3, 4, 5, 6. So, and it uses integers, right? So this clock system is called the integers mod 6. Now, you guys may consider this like a nice math trick that might seem superficial. Like, of course, 5 plus 1 isn't actually 0. We just did a math trick here. Well, I disagree with that, since what we've done here is that we've instead looked at addition not as some linear step progression, but a rotation instead. And this whole system is perfectly consistent with our rules of algebra and arithmetic. It's just that things like 5 plus 1 is no longer 6. For example, I'm here, 5 plus 1 is 6, right? So, sorry, 5 plus 1 is 0, okay? So, this means that if we subtract both sides by 1, right? So we subtract both sides by 1. 1 minus 1, if you look here, 1 minus 1 corresponds to going a step back. So 1 minus 1 is 0. So subtracting both sides by 1, these 1s go away to 0. And we have 5 equals. We might be tempted to say that it says 5 equals minus 1. And we say, aha, we've debunked the system. It gives us a contradiction. But that's not actually true. Because remember, 0 minus 1 is no longer minus 1. 0 minus 1 is 5. It's actually 5. So we don't actually break any of the rules of math when considering this clock modular system. And it's not actually as foreign as we might expect. For example, take the 12-hour clock. Instead of using 12 at the top, let's just use 0. So here I have 0, I have 1, 2, 3, 4, 5, 6, 7, 8, okay, 9, 10, 11, okay. So here is our 12-hour clock, and this is actually just the integers mod 12. So let's say that it's 11 o'clock, and we say, okay, what's 1 hour after 11 o'clock? Well, we'd say it's 12 o'clock, but instead of 12, we are using 0. So it's 0 hour. Now we'd say, okay, what's 1 hour after the 12 o'clock? If you have 12 o'clock plus 1 hour, what is that? Well, we wouldn't say it's 13 o'clock. No, it's going to be 1 o'clock. We have 0, you add an hour, it's 1. So this clock arithmetic isn't very foreign to us. It might seem a bit non-intuitive, a bit non-trivial, but we actually use it from our day-to-day lives, at least if we're using a clock, which I hope you guys are. So yeah, that's all what clockwork arithmetic means. It's some way of forming groups of integers. That's pretty easy. Should have worded that a bit better, because I want to emphasize this here. This was not a group, because if we added 5 by 1, we get 6. That's not in this set. However, if we curl it up, 5 plus 1 would be 0. So we can take any subset of the integers, put it in a circle, and that will be a group. It's just a very easy way to find groups. So we don't have to try to like think of like some random abstract group. Instead, we can just take, okay, here's the integers, take some arbitrary amount of numbers, put them in a circle, bam, we have a group, and we can say that group. So since it's so easy to find groups with this modular system, we are going to use that a lot in group theory, which is why it's very essential to understand to learn group theory. Now, what I've done is I've shown that it's closed. Ignore this bottom part. We've shown that it's actually closed under the operation. Now, we can test this out ourselves, but it's also associative. It's associative. I'm not going to prove that it's associative. You guys can do it yourself, but because associativity isn't really that interesting. However, number 3 is interesting. Does there exist some identity elements in the group such that A, in this case, plus E is A? Well, yes, because if I have 1 over here, let's take 1 for example. 1 plus 1, 2, 3, 4, 5, 6 would be 1. 1 plus 6 is 1. So 6 would be the identity element for 1. But what's really cool is that for each value, for each element of this modular system, there does exist an identity element. For 0, it would be 0. For 5, the identity element would be, I believe, 6, because we'd have 1, 2, 3, 4, 5, 6, right? So there does exist an identity element. Okay, so this is a check, and this is a check as well. But does there exist some inverse elements? Well, the answer is also yes, there does exist some inverse element. Now, note that technically speaking, we can't really go back here. We can't, like, we are only considering addition here. So 0 minus 5 or 0 minus 1, we're not dealing with that. We can deal with that. But if that's the case, then our group would have 2 operations, but we are just considering addition. When I gave an example of subtraction here, it was just to show you how this whole thing is mathematically consistent. So you don't have any contradictions here. So does there exist some inverse operation? As in, if I have some element of this modular system, I have some element of this modular system B, and I add B by some amount, by some value, will I get the identity element? Oops. My bad. The identity element is actually 0. Yeah, my bad. Now, there typically are multiple identity elements. Like here, 6 would be an identity element for 1, but there is a universal identity element, not being 0, because like 1 plus 0 corresponds to not moving at all. 3 plus 0 is 3. So scratch what I said earlier. The identity element is 0. That's a universal identity element. There does exist identity elements for each specific value, but the universal one would be 0. So the inverse element would be, okay, B plus some amount should give us 0. And that is true for each of these inputs. 1, if you have 1, you know, 1, 2, 3, 4, 5, that would give us 0. So for each element, there does exist an inverse element that gives us the identity when operated by addition. Okay, so this means that we do indeed have a group here. Now, is this group an abelian group? As in, is 1 plus 2 equal to 2 plus 1? Well, we can test it ourselves. If I have 1 plus 2 is 3, 2 plus 1 is also 3. So yes, this modular arithmetic thing is an abelian group. But note that it doesn't have to be one to be a group, but it just also is an abelian group. So yeah, That's modular arithmetic. Now there's an extra thing in modular arithmetic. It's called congruency. So we say that A is congruent to B, where B is some number in the modular system, B mod n, if there exists some number that divides A minus B. Now, what does this mean? Well, when you say there's a number that divides A minus B, it means that we can take A minus B, divide it by some number, and obtain some integer number. So if there is some number that divides A minus B, we say that A is congruent to B in that mod system by definition. And from this, we can actually obtain an equation for A. And we multiply both sides by n, and then we add it by both sides by b, and we get A equals kn plus b. Also note that k is a member of the integers. So yeah, that's congruency. It's an extra concept in modular arithmetic. We won't be using it much, but just an extra thing there. The computer science folks will be using it a lot. So yeah, that is what there is in modular arithmetic and group theory. Hope you guys enjoyed this video. If you liked it, please share it. And yeah, I hope you guys have an excellent, great day. Bye.